Hello, this is a screwdriver. You all know what a screwdriver is used for. Now, as I fix the screwdriver into this perfectly drilled hole, how exactly do you think am I able to rotate the screwdriver? Since I'm not pulling or pushing the screwdriver, probably it's not just a force. In fact, it's altogether different, but a related quantity. It is called as a quantity torque. Torque is a tendency of a force to rotate an object about an axis or a fulcrum. The door behind me is fixed at hinges and it can rotate about them. So what do I do to open the door? I apply a torque. As you can see, whenever an object moves around an axis or a pivot, somewhere, some way, a torque is responsible.
A body will undergo only rotational motion if it is fixed at a point or along a line.
So now you know that a torque is a rotational analog of force. Do you know what is a rotational analog of linear momentum?
We know that a rigid body can have a combination of two types of motions, rotation and translation. Translation in a body can be brought about by applying a force to it, which produces a linear acceleration in it. To produce rotational motion in a body, we apply a torque to it. For example, have a look at this door. It is fixed to a vertical axis that passes through its hinges. This means that it can only undergo rotational motion. When a force is applied to the door at its hinges, it undergoes no rotational motion. However, when a force is applied to it at the edge and in a direction perpendicular to it, we see that the door rotates along the vertical axis. When a force is applied at a point on a body to produce rotational motion in the body, we say that a torque has been applied to the body. Torque is to rotational motion what force is to translational motion. The magnitude of torque applied on body depends on the magnitude of force. It is also where and how it is applied on the body.
The angular momentum of the particle in relation to the origin O depends upon the linear momentum of the particle with respect to its origin O and the position. Let's analyze the linear momentum analogy. We know that if there is no external force acting on the system, then the linear momentum remains constant. In other words, the linear momentum of the system is conserved. Similarly, in case of the rotational motion, if there is no external torque acting on the system, then the angular momentum is conserved. For example, take a look at this wheel. It is moving at a constant angular velocity. Now, it is obvious that its angular momentum is constant. However, if I stop the wheel by applying opposite external torque, then the wheel's angular momentum is reduced to zero. Therefore, unless and until an opposite external torque is applied, the wheel's angular momentum is conserved. Whenever a rigid body's angular momentum is conserved, the body is said to be in rotational equilibrium. As you can see later, the concept of rotational equilibrium will help us unravel several mysteries in the world of physics.